new kind of, well, it's not completely new, but these cavities that try to bridge a bit the gap between plasmonic system and fully dielectric system that we call dielectric nanocavities here. So just to present a bit who I am, so I'm working with the quantum photonic in low dimensional system group. We have different activities. I'm working with two other gentlemen, Santry Zhao and Martin Woops. Santry is mostly focusing on nanolasers and moire excitons. Martin is working a lot with collective effects like superradiant, subradiant effects, also quantum emitters coupled to cavities and phonon bath. And me mostly about polariton physics and near field characterization, and also quantum emitters in HBN. My subgroup is formed by this gentleman here, so most of the work is done by Frederick and Laura here. So one of the things is that in Denmark we have this Danish National Research Foundation that gives money for 10 years for a group of different groups with one specific task. Well, the first one I've been part of was headed by Antti-Pekka Jauho, that some of you might know here in Aalto, and where we were working mostly on structuring and preparing, fabricating 2D materials for quantum transport, but also for optical properties. And I learned a lot about fabricating 2D materials and 2D material stacking there. And now we have this new center headed by Jesper Mørk, where we are looking at these peculiar structures that you can see here. And I will talk a bit about this here. So the mission of this center is, as I said, to bridge a bit the world between plasmonics and also conventional nanophotonics. So that means, like, for example, photonic crystals or cavity nanobeams and things like this that are usually can reach extremely high quality factors, but they are inherently limited by diffraction limit. So you cannot focus light smaller than, let's say, half the wavelengths divided by the refractive index in this material. Plasmonics, as we have seen before, also has seen you can get pico cavities as done by Jeremy Baumberg and that Javier showed, where you can have extremely small mode volumes there, but usually they suffer with losses, so ohmic losses, but also absorption also in metals, interband transitions there. And the best quality factor, depending on who you ask, it can go up to, let's say, maybe 50 or 100 or something like this. So the question of this center is a bit what happens if you could actually get really high Q factors, very narrow line width, and also extremely tight confinement of the electromagnetic energy density. And what would be interesting there is to study if we can reach extremely high large Purcell factor to have, for example, dynamical decoupling with phonons, low threshold lasers. And what I will talk about today is about strong light matter coupling. So that means that if you confine, for example, an electromagnetic field, you can enhance strongly light matter interaction. But you can also, if you have, for example, very narrow line width, we hope also that you can also, that can also lead to single photon nonlinearities in this case here. So my talk is divided in two parts. I will talk a little bit first about this extreme dielectric confinement principle, EDC cavities, and then I will show that what happens when we put 2D materials on top of it. That is, for example, here in this case, molybdenum ditelluride. So let's start with the EDC cavities. So these cavities, they are normally designed to try to beat the so-called diffraction limit. And we are not the first. Naturally, there is the group of Michael Lipson, who has been working on this already almost 20 years ago. The group of Dirk Englund also has proposed different structures to do this. And in our case, we have the group of Ole Sigmund at the TU, who is specialized into doing inverse design by topology optimization. And what do you do there is that you have a numerical domain that you discretize, and you start with a given structure, like for example here, a photonic crystal. In the middle, you have an active region that you want, where you want to optimize the mode volume, so the effective mode volume, but also the Q factor. And what you do is that you have discretized this space, and you change the refractive index for each pixels, and you calculate Maxwell's equation until you reach and you calculate what is the response of the system, and you iterate this procedure until you reach the optimized mode volume and Q factor that you desire here. And what you get is these weird-looking structures. We call that the hairy EDC cavities that you can see upstairs here. You can also give to this optimization, to this topology optimization, what is the minimum resolution of your electron beam lithography. So for example, and then you get structures that are a bit less hairy here, a bit easier to fabricate that you can see here, but naturally the confinement is less important than before. Naturally, there are other groups working on that. There is also Ricardo Sapienza, there are also Ortwin Hess and other people. This is actually something that I think is starting to boom a bit now in the field, is to use topology optimization to design these structures here. So once you have this, the problem is also to fabricate them. So there is the group of Søren Stobbe, who is specialized actually in fabricating this structure in our clean room. And here, for example, this is in silicon. So you can see the structure here. This is suspended. It's a silicon on insulator structure. And below that, it's under-etched. So you have also the silicon substrate that is 1.5 micron below, something like this. But you can see this weird shape, but you can recognize, maybe if you know a little bit of photonics, you can recognize some known structures. Like here, for example, you have these rings, and in the middle you have this bridge there where the field will be confined there by, because of high contrast in the refractive index there. We've done that also with indium phosphide. This is the group of Christer Nyvind where they do this. And again, you can recognize here these circular structures that are exactly a bit like a circular Bragg reflector, or bullseye structure, they call that. That is actually effectively confining the light under the diffraction limit, if you want, but this field is then scattered by this little element, this element bridge here, and you can create a evanescent wave there, and therefore you can beat the diffraction limit exactly at this center there. What is interesting is that if you aim for higher Q factor, the number of rings that you will get around this will increase, because actually these rings, they avoid leakage of this mode towards the far field. So you can actually also control the Q factor there. The calculation showed approximately that we can reach approximately less than 10% of the effective mode volume can be 10% less than the effective diffraction limit in these materials. We have cases where people have been in the group of Søren Stobbe where they can reach 10 to the 4 in Q factors in these systems there with the same mode volume here. So now the thing is that we have this structure. My colleagues, like Søren Stobbe, they measure that in the far field. But they are never sure exactly that they will have mode confinement in the middle there. Here you see far field spectra. You recognize these Fano resonances there. This is due to the fact that you have also a Fabry-Perot mode below the cavity that is broadband and interferes with this narrow mode of the cavities there and gives this Fano resonance there. Marcus, who did the structure, came to us and said, you have a near-field optical microscope. Can you measure if we have effectively actually focalization of the field inside in the middle of the structure there? So we used our near-field optical microscope that is from this company Neaspec that many people know probably about. And what it does is basically you have an atomic force microscope here. You focus light on it. And the tip of the AFM is acting as a nano antenna that can focus the light or couple out the light from an evanescent scatterer that is below it. We have different detection schemes, pseudo-heterodyne, and so on, so we can remove a lot of the background and look exactly at very small evanescent fields in our structures there. So Laura, who did the measurement on this structure, well, she spent a lot of time trying to, you have to imagine you have this AFM tip that is going in this structure that is suspended, and the tip naturally can go in the holes. So it's a bit tricky, but we managed to do it. This is the AFM topography that you see, and on the same time that you measure the topography, you can measure also the optical field, and this is how it looks. And so this is the center of the cavity. You can recognize the two eyes. It's a bit looking like Halloween jack-o'-lantern here, if you want. But the thing is that what you see, these eyes, there is an artifact by the tip going inside the hole. I will show you that later. What is interesting is in the center. You have really concentration of the electromagnetic field in the center of it there. And we have measured also the spectrum that also shows this almost Lorentzian-like resonance behavior. The Q factor was slightly reduced from the far field measurement, which is normal. You come with the tip of the AFM and you increase leakage to the far field, but not that much. The effect of the tip is not so important as we feared in the beginning. This is the experiment. So we have hidden the artifacts here just to show that we have field measurement here in the middle, and this is the theory. So we get very good adequation between the two of them. And the guys from the group of Sørenstubbe were extremely happy about this because this was a proof that we have focalization of the electromagnetic fields inside this structure below the diffraction limit here. So here the structure they were measured at telecom wavelengths here. So you can imagine if you look at the scale that it's much, much smaller than the wavelengths of the telecom wavelengths. So we've done that also in indium phosphide, same story. Also we can see this field confinement in the middle. We see some asymmetry that I will explain a bit more in a minute. Here we still don't understand why we have this asymmetry in the resonance peak that we measured with our system here. We suppose that it's maybe still due to the influence of the under-etching, and you have an effective cavity that is created below. But the take-home message there for this is that we can get field confinement beyond the diffraction limit. And this structure have quality factor of 1,000. So it's already 2 orders of magnitude better than plasmonic systems. And you can do better than this. So you can get now 10 to the 4, maybe even 10 to the 5 quality factors depending on what you need to do. Regarding these artifacts, because this was something that was bugging me a bit, so with Frederick, we started to study this a bit more in detail, doing different study with different polarization, landing also the tip of the AFM in the middle of the structure, and look what was the response. What happens is that when the tip of the AFM is going, or the SNOM is going inside a hole, naturally you can create this kind of effective gap between the tip and the edge of the structure. And this makes a small nanophotonic gap that will scatter quite efficiently light. That creates actually these artifacts that you have seen. So naturally, if you think that this is true, then that means that if you avoid going the holes, you should be able to retrieve more efficiently what is the mode structure of the field there. And this is what we did. So this is the structure without HBN. You see again this kind of artifacts here around the holes, even here on the edges. But when you put the HBN on top that is only a few nanometers thick, like 10 nanometers, you see a beautiful mode here, almost perfectly Gaussian-like. And that shows also that, again, we have the field in the middle there. And we have a lateral confinement of approximately 60 nanometers at a wavelength. This is a different cavity here at 1050 nanometers wavelengths. So this is pretty tiny if we think about this. Okay, now we have characterized these structures, and they look really interesting. Is now the story how what happens if you put 2D materials on top of this. And as you see, since we are using it's mostly because of fabrication processes that we have available at DTU, we use mostly silicon or indium phosphide cavities. That means that we don't have that much possibilities for other 2D materials that can be used at this frequency is MOT2 naturally. What is that I will explain a bit later on. Another challenge down that appeared actually during this these different experiments is what we have also other colleagues who grow quantum dots. How do you put a quantum dot here in a gap that is 10 nanometers and your quantum dot is also 10 nanometers? So this is a bit tricky, how you put a quantum emitter there to get, for example, enhance single photon sources or to make photon blockade effects and things like this. So one of the things is that there were already ideas, for example, even before that, is that Christian Schneider was involved in this by Dale Tay also, where they showed that if you have, for example, lateral confinement in polaritons, so with Wanyemot excitons under an open cavity, you can have a bit of enhanced nonlinearities and interactions between the polaritons that can lead to certain level of nonlinearities there. So that was the question, can we do that in our system? And if we can do that, that means we don't need to have effectively to put a quantum emitters like a quantum dot in this structure. It will appear simply because of the overlap of the mode of the cavity with the excitons in this system. It's easily said. The problem is how do you treat that problem? So we had Emil Denning who worked on the theory for this system here, just to give you a bit of an idea. So the problem is the following, is that you have one cavity mode, but you have plenty of different excitons that are just propagating, that have different k-vector, that can be completely delocalized in your 2D material there. So there is a thing is that you use a transformation that is known, for example, in chemistry, but also in phononics and so on, where they use this exciton reaction coordinate. So that means that you recast all this exciton in one collective mode that couples to this cavity here. And this new mode is basically just an average sum over the excitons that are coupling to this mode. In exchange, you have all these excitons that do not couple to that are the residual excitons that are here, that are a loss reservoir, that can also lead to dissipation there. But what is interesting is that when you have naturally small interactions between these excitons, in this new collective mode, you get an effective exciton-exciton interaction that depends actually on the square of the confinement here. What is interesting here is what you see is that the coupling strength between the cavity and the exciton mode, the collective mode, does not depend on the lateral confinement. And that's why actually in many experiments in dielectric cavities coupled to 2D materials, we find coupling strengths that are quite similar there. And this one actually H0, so J0, so the coupling strength depends only on the projection of the electromagnetic field of the cavity on the 2D material. But the, let's say, interaction of excitons over itself here depends on the lateral confinement. So that means that you could tune exciton-exciton interaction if you reduce the confinement size to a level maybe where you can actually get blockade effect. So that means that exciting a two polariton system will be blocked because you will have to add another exciton in this system here, and it will cost you too much energy, and the photon cannot be absorbed there. We have also studied polariton condensation effects, where Maria showed actually that lateral confinement is quite detrimental for polariton condensation, which is normal because in this case, when you have polariton blockade, you play a bit more with the fermionic degrees of freedom of the excitons. The excitons see each other a bit more, and this is detrimental for polariton condensation there. Okay, so for the experiment, just a small disclaimer. This is the goal, right? So we would like to go there. What I will show you now is only the linear response of the system. We haven't had the possibility now to get to the nonlinear response. We used molybdenum detelluride here, and it's an interesting material with a band gap of 1.2, not a band gap, sorry, but the exciton energy is 1.2 electron volts. And this is a single layer of MOT2 that you can see isolated like this. Unfortunately, this material is quite sensitive to air, so we have to encapsulate it with HBN. The cavity we used is a simplified design with a Q factor around 200 or 300 that was designed by George here and fabricated by Mong. Again, you see this circular structure, and in the middle, this bridge where the field will be localized. This is the simulation of the mode that is polarized in one direction here. This is the SNOM measurement that shows that we have the field again, localized in the middle here. So for the fabrication, here we have the MOT2 layer that is encapsulated by HBN below. We have 1.5 nanometer HBN. MOT2 and on top we have approximately 10 nanometers HBN. The sample has been made 1.5 years ago. It's still alive today. We did a check a few days ago and it's still working. So the thing is that it stabilizes MOT2 even at room temperature, and this is why you see the cavity is there in the middle here. The energy of MOT2 is around 1.2 electron volt, and the cavity that we chose is 1.1819 electron volt. The bare cavity mode, you can see it on top here, the bare MOT2, and when we have the two systems together, here they are not coupled, they are far away, this is at room temperature. And now what we will do is to use cooling to redshift the energy of the excitons and overlap it with the mode of the cavity. In the meantime, also when you cool down, the line width of the excitons for MOT2 will also reduce there. I do not show the results in terms of temperature, but in terms of the detuning, where we calculate what is basically the change of energy between the exciton and the cavity here. We have here, for example, the detuning, and we have the energy here, and you see the exciton, how it's evolving, so following the Varshny curve here. And it overlaps around zero detuning here with the cavity mode. This is for the bare system, where we have just extracted what is the maximum of the peak of these modes here. And we have the zero detuning at 40 Kelvin. We use two different cryostats, therefore we have two different frameworks here. So one is a liquid nitrogen cryostat, and the other one is a liquid helium cryostat. This is the photoluminescence measurement, and you see at the place where we should have crossing of the exciton and cavity mode, we see avoided crossing here. And this is a zoom here inside this region here, and you see the lower polariton and the upper polariton that are emerging, and they shift together, sorry. We have extracted also what is the Rabi energy, Rabi splitting between these two, which is around 10.6 millielectron volt, which is 2 times larger than the polariton line width there. So we have 2 Rabi oscillation in the system before it dies. But at least we are in the strong coupling regime here. Just quickly, it's as mentioned many times before, when you do strong coupling, it's always good to check with other measurements that you have also splitting in photoluminescence, but also in reflection. And this is what we did here in reflection, and you see also that we have a splitting with the same amplitude here. We did also polarization, so I said also that the mode of the cavity is very polarized, and you see that we go from the upper and lower polariton here, and we change the polarization, we get the bare exciton energy here, and it goes back to the strong coupling here. So we have here shown strong coupling. With the theory, I will go quickly on this. So we calculated the quasi-normal mode of the cavity, and we evaluated here the projection of the field on the 2D material. These are the Bohr transition matrix for the excitons here, and we find a very good agreement between the theory and also the experiment. So that means also that we're almost there. This is linear response of the system. Now the question is, can we go towards the regime where we could have actually non-linearities in the system? These are different references of people who have studied 2D materials coupled to dielectric cavities or plasmonics. So we are here, so we are a bit away from plasmonics and dielectric in this new regime of extreme dielectric confinement. We need now to go, probably according to our calculation, in this regime to reduce the lateral confinement if we want to hope to see single photon nonlinearities in this system. As an outlook, I would like just to briefly say we are now doing power-dependent measurement, so we can also extract what is the exciton-exciton interaction strength in these systems. We want also to go to higher confinement. This is another work done by the group of Søren Stobbe, where they use collapsed structure to make nanobeams with this bow tie structure. They get down to 2 nanometers lateral confinement. So this could be the kind of structure we would like to make. And actually, we want to study a bit how confinement affects also polarity and condensation, maybe body physics in this, for example, tryons by excitons, how they behave under confinement. So there is plenty of work to do there. So I would like to thank all the people who work on this project, also Batulga and Pavel, who helped me with the low temperature measurement, and actually Frederic and Laura, and Martin von Exter from Leiden, who helped us also to do polarization measurement. Thank you for your attention, and yeah.
Thank you very much for this talk. So it's open for questions or comments. Anton?
Thanks. I was wondering, so you mentioned that the quality factor can be up to 10 to the 4, right?
Yeah.
So when you drop the flake, how much does it drop the quality factor?
We haven't tested this on these particular structures. It's very simple. The reason is that if you want to have strong coupling, you don't want the line width of your cavity to be too narrow. Yeah. Otherwise, you don't overlap with all the photons that are emitted by the 2D materials. So we wanted to have a Q factor that was similar to the Q factor of the excitons at low temperature. So that's why 200, 300 is the right ballpark. So I do not know how much it will be changed for this high Q factors cavity if you put the 2D materials on top. We haven't tested that yet.
And you want to have the Q factor matching the line widths of your exciton because of the broadening, or because of the inhomogeneous broadening, or?
So because either otherwise you are in a regime where it's the decay or the dephasing of the excitons that is dominating the response of the system, and you want to that the dynamic of, or the lifetime of the photon of the cavities is matching also the lifetime of your exciton, to have strong coupling in this system.
All right.
Yeah.
Yeah. And then the second question regarding this size dependence for the condensation. I don't understand then once you shrink your system, then nonlinearities play a bigger role. Therefore, you have this fermionic nature that prevents BC and so on. What you expect if you have rather weak nonlinearities from your excitons? Would it be better to make a smaller size condensate, or?
So these nonlinearities, I think they are detrimental to the formation of this excitons.
Yeah, but if you have a weak nonlinearities, imagine that you have weak or known or completely absent of any nonlinearity.
Yeah, but then you will. Then the thing is that is it really the question we ask also in this paper is it really an advantage to use confinement if you want to study polarity and condensation? So we are not convinced that it's giving any advantage there. In our case.
Okay, simple advantage would be that you need less energy to produce a condensate.
Maybe, but maybe you have a trade-off between confinement and so you don't go to too high confinement so that the nonlinearity is still manageable, but still helps you to get faster condensation. You can read the paper there. I think Maria tried to extract a bit some trade-off there, but yeah, we need to test it also experimentally. Yeah.
Cool.
Thank you. All right, I guess we have to move on. Let's thank the speaker again.